In this video, I would like to go through several examples of how to sketch quadratic functions by identifying key features of the graph. So in each of these problems, we're going to identify these key pieces and use them to sketch the graph that we need. Anytime that you look at a quadratic function and you're planning on doing a graph of some sort or another, it's probably a good idea to go ahead and identify your a, b, and c values. We use them for a lot of the parts of this problem. Remember, the a is the coefficient of the x squared term, which in this case is -1. The b is the coefficient of the x term, which in this case is 9, and the c is the plane number, which in this case is -8. As I look at this particular problem, because my a value is negative, my parabola will be opening down because my a value is a negative number less than 0. That means that when I plot my points, I should be expecting them to come together to make this type of a shape, and the vertex will be a maximum value here. So next question, how do we find the vertex? Well, the formula to find the x-coordinate of the vertex is to use x equals -b over 2a. In our case, our a was -1 and our b was 9, so plugging those into the formula, I'm going to have -9 over 2 times -1. That gives me -9 over -1, and when we simplify that, that's going to give us a value of positive 9, let's try that again. -9 on top, 2 times -1 is -2, and -9 divided by -2 is a positive 4.5. There we go. So that's going to be the x-coordinate of my vertex. The axis of symmetry, if you recall, is that vertical line that you can draw that will give you kind of a mirror image on each side. And the place that that happens, or when that happens, is at that vertical line of x equals 4.5, that vertical line that goes through the vertex coordinate. So here my axis of symmetry is going to happen at x equals 4.5. All right, so we kind of find these two pieces together in our calculations. I found the x-coordinate of the vertex, but I'd really like to find the y-coordinate of the vertex as well, so I can actually plot the point on my graph. Because this is the x-coordinate, we always go back to our home base as the original problem up here, and I can evaluate my function at the point 4.5 to see where the y-coordinate is going to hit there. So if I put 4.5 in for x, you got to put it in both places. I'm going to get -4.5 squared plus 9 times 4.5 minus 8. When we go in to evaluate our function, it's really a good idea. Make sure that only the 4.5 is getting squared because of how my formula was written. So it's negative, put just the 4.5 there in parentheses so that it'll remind you that that's all that wants to happen. -4.5 squared plus 9 times 4.5 minus 8. And in this case, that gives me 12.25 for the y-coordinate of my vertex. So over here, I can kind of make a note. My vertex is going to be at the point 4.5, 12.25. And you know what? Let's go ahead and just start working on our sketch here. So here's my coordinate axis graph. At 4.5, so 1, 2, 3, 4. So in between 4 and 5 here, I've got a nice axis of symmetry. My vertex itself is going to lie at the point 12.25 on the y-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 2.5. So I'm going to get a point right there on my axis of symmetry. So 4.5, 12.25 is that vertex point. I'm expecting the parabola to open down, so it should cross the y-axis, and then it'll cross the x-axis in 2 places on its descent. Let's find out where those are. To find the vertical intercepts, what we want to do is we want to set x equal to 0 and evaluate. So if we put in 0, we're going to have -0 squared plus 9 times 0 minus 8, which gives me -8 for my function. So the point 0, -8, is my vertical intercept, and I can put that on my graph here. 1, 2, 3, 4, 5, 6, 7, 8. So at -8, I'm crossing the y-axis. The horizontal intercepts are a little bit more complex. What we're going to do is we're going to set the output value to 0. So y, or f of x. So what we have here is 0 equals -x squared plus 9x minus 8. And if I want to find what those points are, I need to solve this quadratic equation, and I should be expecting 2 answers. Because there's a squared and an x, we need to get one side equal to 0, which we already have. Awesome. And then we want to go ahead and solve either by factoring or by using the quadratic formula. This is a case where factoring actually works well. I pull out a negative to get my squared term to be positive, and that changes all of the signs of what's inside. This factors nicely to x minus 8 and x minus 1, and then I can set each of my factors equal to 0. Negative can't be equal to 0. That doesn't make any sense. But I can set x minus 8 equals 0 to get 8 as one possible solution. And I can set x minus 1 equals 0 to get x equals 1 as my other solution. So these 2 points here are my horizontal intercepts, and they happen at the point 8, 0 and at the point 1, 0, and I can put them over here on the graph. So let's see, this is 1, 2, 3, 4, 5, 6, 7, 8. So 8, 0 has a point here, 1, 0 has a point here, and notice I've got a pretty neat looking parabola here when I connect the dots. I know the vertex for sure, which is a really important point in the graphing process. And I've got my parabola that's going to extend down this way here. If you really want to be kind of awesome, we know that 4.5 away is the axis of symmetry, so I can use my y-intercept to go 4.5 away in the other direction to get my other point here. And that's kind of a fun way to make sure that you get a couple of extra points so that your graph looks a little bit better when you go to sketch it. So that's really it in terms of using the different properties of a graph in order to sketch a quadratic function. The last thing that sometimes problems will ask you to do is to identify the domain and the range. Keep in mind that the domain is the set of all possible x's, and the range is the set of all possible y's. The domain for a quadratic function is really easy. The domain is always going to be all real numbers, and that's because you can plug any number in for x into that formula and get some sort of an output. The range, however, is always going to be limited because of that squared functioning there. And what happens is we get a vertex, and based on whether my graph opens up or down, I'm going to have some limitations. In this case, notice that the graph goes down forever in the y direction, but the highest it's ever going to be is 12.25. So if we're looking for the description of all possible y's, we want all the y's that are less than or equal to 12.25, and that would give us our value for our range. So the domain would be equal to all real numbers. The range would be equal to the set of all y values such that y is less than or equal to 12.25. So lots of double checking places. Knowing that the parabola opens down is a helpful piece of information. And then as we plot points, we kind of see those pieces all come together. All right, let's try another example here. Our next example is to look at the function y equals x squared minus 4x plus 7. Again, in this case, it's very helpful at the very beginning to identify your values for a, b, and c, because we use them in several places. A is the coordinate of the x squared term, which in this case is 1. B is going to be the coefficient of the x term, which in this case is -4, and c is going to be the plane number 7. Because my a value is a positive 1, because it's positive, it's smiling, and my parabola is, I'm expecting to open up. So this is again because my a value is bigger than 0 this time. To find the vertex is probably the most important part in our parabola process. We're going to use the formula x equals negative b over 2a. My b was -4, so I have negative 4 on top, and it's going to be divided by 2 times a, and my a was 1. The negative 4 means I really have positive 4 divided by 2, and the x-coordinate of my vertex turns out to be 2. As I look, the axis of symmetry always happens at that place where my vertex goes through. So the vertical line x equals 2 is going to be my axis of symmetry for this particular problem. If I want to find the y-coordinate of my vertex, what I have to do is just plug x equals 2 into the formula, because what I'm looking for is I'm looking for the ordered pair combination that goes with x equals 2. So I'm going to put 2 squared minus 4 times 2 plus 7 in here. That's going to be 4 minus 8 is -4 plus 7 is a positive 3. So the point 2, 3 is going to be the vertex of my graph. Vertical intercepts, and again, really there's only one vertical intercept. This happens when we set x equal to 0. So let's plug that in here. If we set x equal to 0, we have y equals 0 squared minus 4 times 0 plus 7, and I end up with 7 as my vertical intercept. So we can think of that as the point 0, 7. You know what, let's go ahead and put some of these points here on our graph and start seeing what's happening here. So my vertex happens at the point 2, 3, so 2, 1, 2, 3, there's my vertex. Vertical intercept is happening at 0, 7. Here's 0, 1, 2, 3, 4, 5, 6, and 7, so there's another point. All right, the next piece that we want to find here is my horizontal intercepts. And again, we find horizontal intercepts by setting y equal to 0 and then solving the equation that gets left behind. So in this case, I'm going to have 0 equals x squared minus 4x plus 7. In order to solve this, because of the squared and the x, I need to either get one side equals 0 and then either factor or use the quadratic formula. Factoring is not going to work because I can't use things that multiply to get 7 to get -4, so I'm going to be stuck using the quadratic formula. In this case, it's x equals negative, well, in all cases, quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so now we start plugging our numbers in. B was -4, and again, I'm grabbing them back up here from the original problem. Oh, sorry about that. The original problem up here. And my values for A, B, and C that I identified at this point. So B is going to be negative, and B was -4. So -4 plus or minus the square root of -4 squared minus 4 times 1 times 7, all divided by 2 times 1. Simplifying this down a little bit, I get a +4 plus or minus the square root of. When I do this, -4 squared minus 4 times 1 times 7, I get -12. And on the bottom, 2 times 1 is 2. And right here, I see I've got a problem because I'm having to take the square root of a negative number, which gives me an imaginary root, which I can't actually graph on my graph. So what does that mean? That just means that there are no horizontal intercepts in this problem. None. And that should kind of make sense, right? If we look here, this is my vertex. I was expecting a parabola that opened up, right? So if we have this parabola that does this sort of thing, it's never going to cross the x-axis at all. So that's great. And that's really not a problem at all. Because I do know that this is the vertex, it's good to have another extra point in there. This is kind of loosey-goosey to only have 2 points. The vertex, of course, is the lowest point in the graph. It is the turning point. We do have that axis of symmetry here that goes through x equals 2. Kind of. But we can, because this was here at 7 and it was 2 away from the axis of symmetry, if we go another 2 away from the axis of symmetry in the other direction, we can get another point, and then we can kind of sketch that in a little bit closer. And well, let's just kind of thicken it up here. It's going to come down like this and then come back up like this. If you want more points to get more levels of accuracy, keep in mind that at this point, now that we have the vertex identified, which is really important, and the intercepts here, we can pick any other point that we want to get more spots pinned down for a more accurate graph. For example, you could put in x equals 1. You could maybe put in x equals 4 or 5 or 6 to get another point on the graph, and then have some additional points for your sketch. Because we didn't have any horizontal intercepts, we didn't have quite as many points as we did in our last graph for making a nice, pretty graph. Real quick to revisit this idea of domain and range. In this case, our domain is going to be all real numbers because that's always the case for our quadratic functions. We can put anything we want in for x. Our range, however, is going to be restricted by the fact of by the location of our vertex. In this case, we want lots of big y values, and the smallest value that y ever takes on is right here at the vertex when it's at y equals 3. So our range is going to be the set of all values such that y is greater than or equal to 3, because it can be 3 or any bigger values from there. So we want to make sure that as we look at that range, look at the graph and see where the vertex is and then where all the other points are relative to that in our graphing process. All right, one last example here. Here we're looking at the function f of x equals 6x squared plus 13x minus 5. Again, great idea to go ahead and identify your a, b, and c. Here a is going to be 6, b is 13, and c is negative 5. Because my a is positive, I'm going to expect my parabola to be opening up. To find my vertex, I'm going to first find the x-coordinate of the vertex by using the formula x equals negative b over 2a. In this case, my b value is 13, so I'm going to have negative 13 over 2 times a is 6. So I end up with the fraction negative 13/12. That's going to be really hard to work with as time goes on. I would recommend just go ahead and divide that on the calculator, and you should get that this is about negative 1.1. You don't need a lot more accuracy than that because our graphs are not that awesome. We're trying to approximate things the best that we can. Axis of symmetry, remember, just is the vertical line x equals whatever the x-coordinate of my vertex is. So x equals negative 1.1 or x equals negative 13/12. Something like that is going to be a great way to describe the axis of symmetry for us. Now, if we want to find the vertex, that only gives us the x-coordinate. So if we really want to pin it down on our graph, we have to find the y-coordinate. So we are going to find f of negative 1.1. So we put that in our equation. Again, back to the original problem. We're just using this very specific negative 1.1 value for x. So I have 6 times negative 1.1 squared plus 13 times negative 1.1 minus 5. Well, that looks pretty complicated for me, so let me pull up my calculator here and see what we get. All right, so we're going to do 6 times negative 1.1 squared, and again, using parentheses is really important here because now this negative 1.1 is part of the x, so it all has to be part of what gets squared. So I'm going to have that plus 13 times negative 1.1, and then minus 5. Oh, I must have typed something in wrong. Let's see what we got here. Oh, I think I hit a negative button or something. Let's try again. 6 times negative 1.1 in parentheses squared plus 13 times negative 1.1 minus 5. That gives me a negative 12.4. Let's see, 12.04. So let's just say, yeah, we'll just say about negative. We'll just write 12.04. That's fine. So our vertex is going to be happening at about negative 1.1 on the x-coordinate and about negative 12.04 on the y-coordinate when we go to graph that. All right, let's see what happens next. The next piece that we want to look at is the vertical intercepts, and again, just really one vertical intercept. So we're going to put 0 in for x, and when we do that, we end up with our function value 0 plus 0 minus 5, negative 5. So my vertical intercept is going to happen at the point 0, negative 5. The last piece that I need to find is my horizontal intercepts. In order to do that, what I want to do is set y, or my output, equal to 0 and see what happens. Here I get 0 equals 6x squared plus 13x minus 5. And because of the x squared and the x, I can't solve using traditional methods because I can't get those terms together. So I need one side equal to 0 and then either factor or use the quadratic formula. This one actually does factor without too much trouble. In this case, we can get 6x squared by using 2x times 3x. And if we need 5 times 1 as factors of 5, and we need one of them to be positive and one of them to be negative. So I think if we do this way, 5 and 1, that'll get us 6x squared minus 2x plus 15x, which gives us a positive 13x, and then 5 times negative 1 gives me a negative 5. So that works out great. Then I can set each factor equal to 0 and come up with the 2 horizontal intercepts for this particular problem. In this case, I'll minus 5 from each side, divide by 2, and I get negative 2.5 for an x-coordinate. Over here, I'm going to add 1 to each side, divide by 3, and I get 1/3 as my other coordinate here. So those are my horizontal intercepts, 1/3, 0, and negative 2.50. So let's go ahead and try to sketch all of that exciting information here. Kind of see what happens. At negative 1.1 and negative 12, 1, 2, 3, 4, 5, 6, 7. Oh, let's scroll down some more. 8, 9, 10, 11, 12. So I'm going to have a point down here. My axis of symmetry will go through that. At 0, negative 5, I've got a position point there. At 1/3, 0, so up here I've got 1 point, and at negative 2.50 here I've got another point. And if you see, we can kind of get that it's coming up this way, and it's coming up this way, and there's a fairly good graph of my function. Based on this, I can identify the domain and the range. Again, the domain is all possible values of x, which is all real numbers for a quadratic function. The range is going to be affected by our by our vertex. In this case, our vertex, that low point down there was negative 12.04. We want any y value bigger than that. So all y values greater than, make sure we make that negative 12.04. And again, that's just kind of an approximation, but that's going to be close enough for our purposes here in this class.